speaker will be Andras Kroo from Budapest, and he will speak on the Bernstein-Markov property for multivariate polynomials. Please.
Thank you. Well, I'm one of the last speakers, so I think it's only appropriate, maybe on behalf of all of us, to thank the organizers for the great meeting. It was a big pleasure to be here, inspiring atmosphere. I actually was invited a couple of times before, but never made it. So this is the first time for me to be here. Now I finally realized what I was missing. So, thank you. So I will start first with some motivation. What is the Bernstein-Markov property? What I mean by that? Actually, my talk is only loosely connected to discretization, but there is a connection because the Bernstein-Markov property that I'm talking about is, roughly speaking, that's a Nikolsky type inequality. And we have seen it in many lectures during this week. Nikolsky plays a very important role in discretization, even though I'm going to break a rule because in the discretization that we have seen before, the Nikolsky was always needed with the order of square root of dimension. And here, the Bernstein-Markov property that I'm talking about, roughly speaking, it means that you have a Nikolsky with sub-exponential increase. So it doesn't increase exponentially, a little slower than that. But yeah, we'll see that this allows to consider very, very general sets. So first of all, let me start with just a few remarks where this problem is coming from. So my talk will be concerning only polynomials. So capital P and D's, polynomials of D variables, real algebraic polynomial of total degree at most n. And then we have the usual reproducing kernel on a set K with some weight omega. So K is a compact in the D space. The interior of K is always assumed to be non-empty. And this is a non-negative weight that we are using here. So this reproducing kernel is well known. It works for every polynomial in P and D. And the main thing for me for this, from the point of view of this talk, is that if you look at the reproducing kernel on the diagonal, so you set x and y here to be equal, then this knxx satisfies the following extremal property. It just equals the sup of the value of the polynomial. But when you sup the value of the polynomial at point x under the condition that the weighted L2 norm of this polynomial on the compact K is 1. And you take the sup of all polynomials of degree at most n. And the reciprocal of this quantity, that's the classical Nth-Christoffel function of our measure on the compact set K. Now, as I mentioned, my major concern will be to describe sets on which this Christoffel-Darboux kernel on the diagonal has a sub-exponential increase, which is equivalent to saying that the Christoffel function has a sub-exponential decrease because it's just the reciprocal of k and x. And just to motivate this problem, I could refer to this monograph by Stahl and Torik. There are several chapters in this monograph which kind of show that the sub-exponential increase of this k and xx is very important from the point of view of studying the asymptotics of orthogonal polynomials. And this is exactly the property that I'm going to call Bernstein-Markov property. I'm going to give the formal definition in a minute.
The property of width? Of width?
Weight?
Width or weight function?
Weight. Weight and the domain. So it depends on the weight and the domain. And just to mention another recent monograph, which appeared only a couple of years ago, and the same property plays a very important role in that book, and it is shown to be useful in some problems with data analysis. Actually, I also was working with Doron Lubinsky about 10 years ago on the universality of Christoffel functions, and we ran into the same question of verifying sub-exponential increase of this kernel. Okay, so here is the formal definition now. So I'm going to make it in a little bit more general context of LQ, not necessarily L2. So LQ, Q is any parameter between 0 and infinity. This is LQ with respect to non-negative weight omega on a compact K which has a non-empty interior. So as I said, this weight is non-negative, integrable on K. And we are going to say that the Bernstein-Markov property holds for the given point x in the domain if for any parameter q between 0 and infinity, this lim sup is less or equal than 1. So what we are looking here at the value of the polynomial at x, we divide by the LQ, weighted LQ norm of the polynomial. We take the nth root of this quantity and we lim sup over the polynomials with degree going to infinity. And this lim sup being less or equal than 1 essentially means that the value of the polynomial at point x does not grow exponentially relative to the LQ norm of the polynomial. Or you can do the same uniformly on the whole compact K. So we'll say that the Bernstein-Markov property holds on K if you, instead of evaluating just at a single point, you take the uniform norm on the compact K divided by the weighted LQ norm, take the nth root again, sup over all the polynomials of degree at most n, take the limit as n goes to infinity. If this limit is 1, this limit actually is always bigger or equal than 1, evidently. But if it's exactly 1, that means that the uniform norm does not grow exponentially relative to the LQ norm. So this is now the formal definition. I actually am not sure why in the literature it is called Bernstein-Markov. So I was thinking, you know, which term to use, because, for example, in the Stahl-Totic book, they call it regularity of the measure. And well, regularity of the measure, sometimes it is used in some other relation. Anyway, so I'm sticking to the Bernstein-Markov, even though the first interesting result was done by Erdős and Turan about 80 years ago. And they verified that in the univariate case, univariate polynomials, if K is a finite union of intervals, then the Bernstein-Markov property holds for any weight which is positive almost everywhere on this finite union of intervals. So the interesting thing here is that the problem is now kind of weight independent. So if you take any weight which is positive almost everywhere, then you have this Bernstein-Markov property. Okay, typically, if you look at some model domains, like balls, simplices, cubes, and you look at some standard Jacobi weights, then these quantities are very well known and calculated. Roughly speaking, this kernel, KNXX, is of order n to the 2d. D is the dimension, and that holds on the whole compact K. For this standard domains which I mentioned, you always get a Shapur bound n to the order of order n to the order d if you are in the interior of these domains. And it is also known that outside of the domain you have an exponential increase. So that basically means that the crucial problem is about the boundary, because inside the domain, well, as I said, my point of interest is sub-exponential increase. Of course, a polynomial increase is sub-exponential. So inside of the domain, I'm done. Outside of the domain, the increase is always exponential. So the only question is the boundary. So what happens on the boundary? Okay, so I hope I kind of made enough motivation for studying this problem. So now we are going to consider this question. What kind of structural properties does the compact set in D has to have in order that for non-negative weights, and which non-negative weights the Bernstein-Markov property holds. So now I'm going to introduce a somewhat technical definition here, and this is the definition that I'm going to use. It's roughly speaking called analytic connectedness. So what happens here for the compact K and for the point X, actually right here it's in K, but essentially X has to be on the boundary, of course. The question is if I can connect my X to the interior of K by an analytic curve. That's what I am asking. So by analytic curve, I mean a curve which maps 0, 1 into this space, and analyticity is assumed in the neighborhood of the interval 0, 1. So this omega delta is a delta neighborhood of 0, 1. So capital A delta denotes the curves which are analytic in this delta neighborhood of interval 0, 1. And I have a normalization, which is not very important. So all these curves are bounded by 1. This normalization can always be achieved by a dilation, so it doesn't restrict my generality. So, and then I'm saying here that my point is analytically connected to domain K if for some delta I can find a curve which is in class A delta. So it's an analytic curve which originates from point X and belongs to the interior of K for every t bigger than 0, less than 1. And we use this property already independently with Stotic and myself, and it was used in the study of sub-exponential growth of Markov factor. Now I'm going to define a somewhat more general notion here of weak analytic connectedness. So I'm going to make a picture, maybe it will be more clear. So one has to think about a domain which is kind of very caspidal. So you have a point here which you cannot connect with a nice curve. So this is my point X on the boundary of my domain K. And on the previous slide, the condition was that I can find an analytic curve which connects my point to the inside interior of the domain. And now I'm going to a little bit generalize this property because I am going to give you an example to show that you cannot connect. Sometimes in a very nice domain, you cannot still make this connection by an analytic curve. So what happens for some domains that your curve is going to stick out on a little piece. Let me make it red here. So no matter how hard you try to connect your point with the interior of the domain, there is a little piece, this red arc, which is going to stick out. And but in case if this arc is not too large, if it's small relative to that delta which characterizes the analyticity, then I'm still good with this domain. So this is the definition I'm going to give now, and it will cover more general domains. So here is the main definition for my talk. I have a compact K, non-empty interior, and I have a point X, which is essentially on the boundary of K. And I'm going to say that this point is weakly A connected to K. If there exists a function phi of t, which positive function going to 0 as t goes to 0, such that no matter how small delta I choose, I can find an analytic curve with this parameter delta. So delta controls the neighborhood in which the curve is analytic. And this curve is going to originate from X, so at 0 it equals X, and it is going to be in the interior of the domain, not for every t, but only for t between delta and phi of delta, delta phi delta and 1. So I'm allowing now this curve to be outside a little bit, but since this phi delta tends to 0 at 0, this quantity here, this red arc, is a little or of delta. So this exceptional set where the curve sticks out is not too large. And then my point is weakly analytically connected. And another quantity that will appear sometime in what follows is the maximal ball which is centered at my curve and which is contained in K for every such t. Well, if my analytic curve here for certain parameters is in the interior, then of course I can find balls centered at this curve which are inside the domain, and this R delta is the radius of the largest such ball when the balls are contained in K for every t between 1 and delta phi delta. So some of my results will be quantitative. So in order to give a quantitative result, I'm going to need this phi and r. Okay, so that's the notation, the definition. And as I said, this definition allows to consider more general cusps. Of course, any weakly connected point is A-connected as well, because the definition of A-connectedness means that the whole curve is inside of the domain. So anyway, it's a little technical, so let me give you an example to show why am I doing all of this. So I'm going to look at a very simple domain now. That's the domain on the plane, points on the plane between two curves, A times x to the alpha and B times x to the alpha. So y is between these two curves, x is between 0, 1. So that's my domain. So I'll make another picture here. That's 0, 1. And the crucial point, of course, is the origin. That's the cusp. That's the one that I want to deal with. And the question is the cusp connected analytically to the domain or not? And it's kind of simple that if my parameter alpha here is some real number bigger than 1, that's what makes it to be cusp. If I take alpha to be 1, I have no cusp. So alpha bigger than 1 means a cusp. Now, if this alpha is rational, then you can easily connect the origin to the interior by not even analytic, even a polynomial curve. So you take such a polynomial curve. If your alpha is p over q, and you take this curve, then you connected your cusp to the origin, everything is fine. But what happens if alpha is irrational? If alpha is irrational, it's not hard to see that you cannot connect this cusp analytically. So no matter how much you try, and that's when my notion of weak analytic connectedness is coming into play, because it turns out that even for irrational alphas, you can connect the origin to the interior of this domain so that exactly this phenomenon is going to happen. Some little piece is going to stick out, but it's going to be small relative to that delta which characterizes the analyticity. So this somewhat more general notion helps to deal with domains, with these irrational domains. Okay, so here comes basically the main result that I wanted to present. And it says that if I have a compact in the D space, any q between 0 and infinity, and I consider any weight which is positive almost everywhere on K, then for every weakly A-connected point, x in K, the square root of 1 over n of this ratio, the limit loop is going to be less or equal than 1. So you do have a sub-exponential increase at point x, and well, I don't remember if I introduced the notion of the whole compact being weakly A-connected, but it's kind of natural. If you have this weak analytic connectedness at a single point, you can extend it to the whole compact if everything works uniformly on the compact. So you can connect every point on the boundary by proper analytic curves. So if your compact is weakly A-connected, then you have basically, this is essentially a Nikolsky type inequality with a sub-exponential increase. One question that you may ask, why are the analytic curves here? Can I do something less than that? Can I connect my cusps by C infinity curves instead of analytic? And it turns out that the answer is no. So the analytic connectedness is kind of a crucial property here. So by C infinity connectedness, of course, I mean that you have a point on the boundary which can be connected to the interior of your domain by a C infinity curve instead of analytic curve. So the next statement here is a converse result, which says that for any q between 0 and infinity, I can construct a compact K in D space so that the origin is C infinity connected to the interior of K. And nevertheless, for a certain sequence of polynomials of degree nk with nk going to infinity, you have a reverse inequality with a fixed constant m bigger than 1. So the value of your polynomials at the origin is going to exponentially increase relative to the LQ norm of the polynomials. Actually, the weight is 1 here, so that's why it's not present. My previous statement works for any positive weight, which is positive almost everywhere. Here I just take weight 1 and construct a compact for which we don't have sub-exponential increase in Nikolsky inequality. So in that sense, analytic connectedness is necessary here. You cannot relax it further. Okay, now I'm kind of done with the Bernstein-Markov property. I'm going to show some applications of the same property of analytic connectedness to some other problems. And the first problem I want to look at is a Markov type problem when you study the growth of the derivatives of the polynomials on an analytically connected set. A Markov type problem tells you that if you basically have an estimate of the uniform norm, this is the Markov type estimate in a uniform norm, you can estimate gradients of multivariate polynomials uniformly on a compact K by the norm of the polynomials on the same compact with some asymptotics n to the m for nice compact sets. Nice here means, for instance, if your compact is polynomially connected. So if instead of analytic curves you use polynomial curves of fixed degree, which is bounded from above, then you always have something like that. So for instance, for Lipschitz domains, you are going to have n squared here. For some domains which are cuspidal but polynomially connected, your n squared can go up to n to the 10 or whatever. But if your domain is polynomially connected, you always have a polynomial increase for Markov constant. And there was a paper which actually Vilma Stotic and myself, we did it independently, and we showed that analytic connectedness of the domain implies that Markov factors always have a sub-exponential growth. And I'm going to now state a result which extends this for weak analytic connectedness. So this is something that is going to work now for this irrational cusp that I mentioned here. So now, basically the same setting, I have a compact, and I assume that my compact is weakly A-connected at point X. Then whenever I take a polynomial degree at most n in the variables, the derivative of my polynomial divided by the uniform norm of the polynomial takes the nth root of its sup it over all polynomial degree at most n. The limit is going to be 1, which essentially means that you have sub-exponential increase. And I want to show now a quantitative version of this statement. When I gave the definition of A-connectedness, I used this function phi, which was essentially describing the length of that red curve, red arc, which is sticking out of my compact. And I also used the quantity r delta, which was giving me the radius of the largest ball, which is inscribed into my domain there. So if I have these two parameters, phi and delta, I can set up this equation. I have a phi, I have an r, And the solution of this equation, I denoted by delta n, is going to be something that goes to 0 as n goes to infinity. And it turns out that in this generality, you are going to have the following Markov type estimate. The derivative of your polynomial at x is going to be bounded by this exponent times the uniform norm of the polynomial on the domain k. And as you can see here, delta n being the solution of this equation, and it's easy to see is going to 0. So what I have here in the exponent is n times something that goes to 0 with n. So it's a sub-exponential increase. It's kind of interesting to look what happens at this domain that I was talking about before, this irrational domain on the plane when y is between these two curves with possibly irrational alpha, which is bigger than 1. For example, for this specific case, one can show that the condition of weak A connectedness is going to hold with phi delta being of this form, r delta being of this form, two exponentials. So this delta n, which I had on the, on the previous slide, you can compute explicitly, and it turns out that for this domain, delta n is going to be of order 1 over log n. And then if you use the previous statement that I had, turns out that for this domain, omega alpha, even for irrational alpha, you're going to have this Markov type estimate for the derivative of the polynomial uniform norm, n to the power c log n. So again, something that is sub-exponential. And that was actually, for this specific domain, this inequality was done in a joint paper with Tomáš Erdei about 20 years ago. This result is kind of recovered here then. But for instance, if you have a domain of this sort or any other domain which is weakly A connected, and these two functions r and phi have polynomial growth, so you kind of know some information about them, then you can compute the Markov factor explicitly from the previous statement, and you're going to have a polynomial increase that you can write down. Now, what I had before, I had a Nikolsky type statement of inequality for compacts with weak A connectedness, and I had a Markov in uniform norm. So you can now combine the two of them, and then that will give you a Markov which mixes the norms. And that's my next statement here. So basically, it's a simple corollary from the two previous estimates. If my compact is weakly A connected, and I have now two non-negative weights, mu and w, mu is just non-negative, w has to be strictly positive almost everywhere on the compact, and I have any two p and q between 0 and infinity. What I do here, I take the norm of the derivative of the polynomial in LQ relative to weight mu, divided by the norm of the polynomial in LP relative to the weight w. Then the sup of the nth root of this is going to be 1 at infinity. So again, the size of this derivative is going to be sub-exponential relative to this norm. Any two LP norms and any two weights, basically. Okay, it's 10 more minutes, right?
Yeah.
Let me show you another application of what I am doing here today, and that's related to a Chebyshev type problem, which concerns estimating a polynomial at a point outside of your domain when you have a uniform norm known on the domain. So I'm taking a polynomial of degree n. I know that the uniform norm on the compact K is 1. And the question is, how big can be this same polynomial at a point x outside of my domain? Well, if you take the point outside, the size of your polynomial is going to increase exponentially. That's clear. But if your point is very close to the domain, as you approach the boundary, something a little bit more delicate may happen there, and that's what I want to pinpoint here. But first, let me recall this classical thing that for univariate polynomials, if you take a univariate polynomial degree n, then the value of your polynomial at any point outside interval -1, 1 can be estimated from above by the value of the Chebyshev polynomial at that same point x times the norm of your polynomial inside the interval -1, 1. So it tells you basically that the largest possible value that you can get outside the interval is the value of the Chebyshev polynomial outside the interval. And if you use some rough asymptotics for Chebyshev polynomials outside of the interval, from here you can go to this estimate that the value of your polynomial outside the interval is going to be can be bounded by this exponential times the norm of the polynomial uniform norm on interval -1, 1. The point here is that, well, you have exponential growth relative to n, of course, but as you get close to the boundary, when x approaches 1, the square root gets very small. So in the vicinity of the boundary, you get something more delicate. Actually, solution of this same problem is known for convex bodies, and I'm going now to show you an application for this weakly A-connected sets. So let again K be a weakly A-connected compact. Functions phi and r, they were specified in the definition, so they are given to me somehow. And now I take any polynomial of degree n with uniform norm 1 on the compact K, and then it turns out that at any point y outside of the compact K, the value of your polynomial can be estimated like this. Well, I don't have the norm of the polynomial because I normalize it to be 1 here. So you have this exponential again, c times n. Now the interesting part is this cubic root. Well, gamma is just some function going to 0 at 0. So gamma is the inverse of this function r and phi. They are coming from the definition of the weakly A-connected set. So the point is that gamma goes to 0 at 0, phi goes to 0 at 0. So this cubic root that I have here is something that goes to 0 at the boundary. So you can kind of get more delicate estimates for your polynomials outside of the compact set K if you are close to the boundary. For instance, it's just a simple implication of the previous statement. If the function r and phi, they have polynomial growth, something like t to the alpha, t to the beta, you can compute this cubic root and you'll get this type of estimate. Again, exponential estimate, but n is multiplied by the distance from your point to the boundary of the domain. So within the boundary, you get a little bit more information. And a similar thing can be said about the so-called Csiák extremal function, which is used very much in the pluripotential theory. It is, this function is somewhat close to the Chebyshev problem that I mentioned before, but the point here is that you make it independent of n. So the Csiák extremal function at any point x in Rd is defined like this. You soup the value of the polynomial of degree at most n at x, and you take the nth root of that, and you soup over all polynomials of degree at most n, which are bounded uniformly by 1 on the compact K, and you also soup over all n, so that makes your function independent of n. And well, one of the basic questions about the Csiák extremal function is how does it behave on the boundary of the compact K. On the compact K, the Csiák extremal function is almost always 1. Outside it is bigger than 1. The question is what happens around the boundary. And in the pluripotential theory, it is important to know if this function is continuous on the boundary. And for this weakly connected sets, I get the continuity of the Csiák extremal function. Also, I get an explicit estimate of the modulus of continuity of this function. So basically, here is another corollary. If my set is weakly A connected, that this CCAC extremal function is always going to be between these two quantities, 1 and 1 plus this cubic root. The point here again is that this complicated function here that I have goes to 0 when the distance from x to the boundary of the compact K goes to 0. So you can see that my function, the CSAC extremal function, is going to be continuous on the boundary. So yeah, these are the few papers that and monograph that I mentioned today, starting with paper by Erdős and Turan, which was kind of the first on this Bernstein-Markov property, a paper from 1940. And the results of this talk, they are in a manuscript that I just submitted recently. So thank you for your attention.
Thank you very much for the interesting talk. Comments, questions? Behind you first. You.
So what happens for fractal domains? Do you have any of the property for fractal domains?
Fractal domains. If they are analytically connected, then yes. But
Immediately analytically connected?
Hmm?
They are analytically.
They are. Well, you know, it's a general condition. If you have a fractal domain which is connected in the proper way, then the answer is yes. But one has to check the.
Okay, but are there some domains that are not?
Hmm?
Are there some domains like fractals that are not connected, analytically connected?
Well, one domain that I know that is not connected, and I never showed you a picture. I mentioned that C infinity connected. This does not suffice, and that connect domain. Well, I can kind of roughly show you the picture how it is going to look like. Not very nice. So it's kind of a oscillating snake, and you have to make, of course, the interior non-empty, and you have infinitely many oscillations as you go down to the origin, and the oscillations is kind of delicate. The oscillations, the size of them can be chosen in such a way that you cannot inscribe an analytic curve to connect to the origin, but you can inscribe a C infinity curve. Well, I don't know if this is fractal or not, but this is the kind of domain for which the thing falls apart.
Further questions? Please.
About the connections of your result with discretization, it's in one direction is clearly it implies this sub-exponential discretization in this subspace.
Right, by sub-exponential, this is the number of the points. But
yeah.
In most cases, the results are much better than a sub-exponential, right? Because in many of those discretization results have optimal number of points asymptotically. So in that sense, it doesn't help, maybe, I don't know.
Oh, but if the weights is very bad and the domain is very bad, it's could be studied.
Usually in the discretization results, it's a priori assumed that you have an Nikolsky of the form square root of the dimension, right? But then you still need to check if your domain satisfies it or not. So in that sense, yes. At least it gives you a sub-exponential.
No, in the uniform norm, you don't need any Nikolsky and nothing, but you have exponentially big number of points. So and you can, if something like your condition is satisfied, it's sub-exponential.
Okay, thank you. So it's not that useless after all.
Yeah.
Okay.
Further questions? Sergei?
So I have a question about theorem 4, the Remes report you mentioned.
Remes. Well, I never called it Remes, but 4, yeah.
Yeah, so I guess an interesting question would be the dependence on the dimension. So I guess the small c depends on the dimension?
Yeah, the dimension, the d is in the constant, yeah. And I never checked, you
Do we
know.
know the dependence on this?
No.
Supposedly it
No,
has
it's
to be
pretty-
linear, right?
Hmm?
Supposedly it has to be linear.
Wow. That would be nice, but I am sure that if I go through all the things that I was using,
That wouldn't be.
it is not going to be linear, I don't think so.
have time for more.
How precise are your inequalities with cubic roots?
No idea. You know, these things are kind of general because I was trying to aim for a very general compact set. So I have doubts about the exactness of the cubic roots. So.
Yeah, you partially already answered my question. I was curious about the negative result with C infinity connectivity. So my question was, what is the bad body? I guess it's this.
Yes.
What are bad polynomials? What happens there? So not polynomials, but the norm is bad, right? The norm of the domain is bad. Or what?
Well, the polynomials have to be bivariate.
Mm-hmm.
So basically, you have to construct very bad univariate algebraic polynomials and then make them bivariate. So it's not easy to explain, but
Okay, go ahead. Silly question. So in theorem 4, do you have something similar if you just choose K to be a sufficiently large but a finite set?
oh, so you want to replace the uniform norm by a discrete norm there?
Yeah, but just the K only contains finitely many points.
Okay.
So there's no collection at all.
Well, it's a good question. I never thought about it, but you know, if you take a good discrete point set,
Yeah, very large.
yeah. And never thought about it, but it's an interesting question. Yeah.
So that's combining remes and discretization in the same.
Yes.
Further questions or comments? Please.
Is, for example, for a bounded Lipschitz domain inside, is it needed?
Can you please speak up a little bit? I'm an old man and I'm a little deaf.
If we consider, let's say, a bounded Lipschitz domain, is it known that you will always have polynomial bounds? So you mentioned this On to the D was very special, but is it known?
If I always have polynomial bound for what?
For bounded Lipschitz domains for the function inside the domain.
I'm not sure I understand you.
Okay, for this, for the Christoffel function for the inverse, is the polynomial bound for general bounded Lipschitz domains?
Polynomial bound in Markov inequality, you mean?
Oh, yeah.
Yes, the answer is yes. Yeah, the Lipschitz domain, for the Lipschitz domain you'll have n squared. So the power of n gets worse when you have cusps, but if you don't have a cusp, then it's an n squared.
Okay.
Those, it seems, all questions, so let us thank the speaker again.